Alright, so this video is going to be talking about section 5.4. Specifically, just the fundamental theorem of calculus in general, which in this book is spread over 2 sections. Fundamental theorem of calculus. Okay, and so the idea here is this, is that we've been doing, or we've seen this just a little bit. So up until, I shouldn't say that. In Calc 1, you talked about derivatives. Okay. The fundamental theorem of calculus is the theorem that marries derivative calculus, or differential derivative, or what the big kids call differential calculus, marries it to what we're going to be studying about in this class, which is integral calculus. So this theorem is what puts the two halves of the pie together. Okay, so up to this point we've been basically doing the derivative part of it. Now we're going to move into the integral part of it. This is the theorem that says, hey, well, this is what they are to one another. Okay, so we talked a little bit in the last video about how if you have a formula like this, f of t dt, or maybe it's f of x dx, not really that important. The fundamental theorem of calculus part 1, if you will, says that when you do this, you take the antiderivative of f of t. That's denoted by cap f of t from a to b. And so that's f of b minus f of a. Okay, this is one part of the fundamental theorem of calculus. It's a big part, but it's not the only part. This basically is saying to us that the integral is the inverse function of the derivative. Because if you'll notice what we just did there, we did the antiderivative and then we evaluated it. Okay, so in essence this is what it's saying. It's not all of what it's saying, but that's a big part of what it's saying. Now for two things to be inverses, it has to work both ways. In other words, the derivative had better be the inverse of the integral, because right now that's not necessarily true. And so the second part of the fundamental theorem of calculus says this. If you have a function, let's say it's f of t dt, and you want to integrate it from some a value up to some x value. Now what does that mean? Now notice that this variable here, these t's and this x cannot be the same. You cannot have f of x dx and integrate it with respect to x. It doesn't make any sense. So the idea is this. You have some x equals a value here. You've got some function doing whatever it's doing. And so here, this x equals a, this is this lower value down here. Okay? So that's great. You know, if you integrate this thing, you're going to find the area under this curve over to here. Just, you know, x. Okay? But that's not what I'm asking about. In this equation, what I'm going to do is I'm going to take the derivative of this thing with respect to x. Wait a minute. What happens, do you think, when you take the derivative of an integral? Well, some people would say it just cancels out. And those people would be pretty correct. But let's think about this for a minute. If those things cancel out, you're left with f of something. F of something. Remember, this guy here is a derivative, or if you will, a rate of change. Right? And a rate of change only makes sense if you evaluate it at a point. Correct? I mean, it only makes sense to have it to be a function. Now, a function of what, you might ask? Well, turns out it's f of x. Okay? Now, notice it does not matter what this constant is down here. It could be 7, could be 12, could be 14. I'm not interested in what the rate was at 7. I'm interested in what is the rate of change here, right here at x equals at x. So this is my value. Okay? What this is saying to us is, in essence, the derivative is the inverse of the integral. Okay? Now, we can do this a bunch of different ways. You know, here's an interesting one, for instance. We'll do a nice easy one. It's the sine of 3t minus 2 or something, dt. And you're like, let's take the derivative with respect to x. Okay, cool. So that will cancel and you'll be left with the sine of 3x minus 2. That's it, man. Nothing to it. Now, if they were all that easy, I would be done with the video right now. Some of them get a little messier. Some of them get a little messier. For instance, suppose some wackadoodle tells you to do it this way. They tell you to go from x to 2 of square root of 3x minus 7 or something. Plus 5x, just for a good, not 5x, these should be t's, sorry. Plus 5t. I said t, there you go. dt. And I want to take the derivative with respect to x. Okay, I cannot do this. I cannot do this. This needs to be written so that the x is on the top. Now, can I do this? The answer, of course, is, well, sure, you can do it, Jay. But you have to change the sign because you're integrating in the wrong order, the opposite order. Okay? So what is the What is the derivative of this? Well, once again, this and this cancel one another, and you're left with negative. It's going to be 3x minus 7 square rooted plus 5x. And so, of course, if you do that, it's going to be negative this minus this. Piece of cake. Now, where do we use this in the real world? Good question. So, you really don't. Okay? In general, you rarely use this, quote unquote, in the real world. This is a theorem that without this, calculus really wouldn't exist. Okay? It's one of the underpinnings of calculus, and you can be happy that it does work. Without it, calculus really would not be what it is. It wouldn't work the way we think it should. Okay, now this one here is a little strange. Okay, let's do it. So take the derivative here. Notice we're going from a constant. That's good. Up to a value. That's weird, but yes, the right value. So these guys cancel. So you're thinking, I'm going to do this. And I think, well, you're partially right. I would say you're partially correct. Okay. However, this has now become a what? This has become a function in a function. Are you with me? So you just took a derivative of a function in a function. That means the chain rule is at play, yes? So when we do this, we're going to have to multiply by a 4 here and here, because that is the derivative of this inside piece. So I should end up with 12 ln 6 minus 8x plus 24 times 4x squared. I guess I could take that a little bit further, of course. Oops. Which, of course, that's 16. What is 16 times 24 today? 24 carried 2, 144. That makes sense. Sure. 284. I'd buy that for a nickel, I think. And there you have it. Okay. This one's pretty cool. This one actually makes me happy every time I see it. You're like, Jay, you have a weird sense of making you happy. It's true. You're not wrong. Watch me just put a little g of t in here. Notice it doesn't make any difference what that function is. I'm just going to replace the t with these guys here. Now, ooh, this is weird. This feels strangely dirty or something. Think about this for a minute. If I told you, here's a function. Let's call it f of t just for a good time. And I want to find the area between 6 and 8. The integral from 6 to 8 is equal to, I should write f of t, don't be lazy, is equal to the integral from 0 to 8, which is from here all the way down, minus the integral from 0 to 6, f of t dt. that would be this region in here. You'd get rid of that, and you'd be left with the part that you're interested in. When you see one that looks like this, you're going to have to do the exact same thing. So it's going to be d dx. Oops. d dx. I'm going to go 0 to 3x. G, I think of t it was, dt. Minus the integral from 0 to 2x. G of t dt. Okay? Now, think about that for a minute. We're taking the derivative of everybody inside. So the rules for integrals say that you can do them in pairs. And remember, why is that? Because these guys are just limits, yes? So the limit of the sum of the limits, yes? Same thing is true here. The derivative and integrals are both just limits. So I can do this. So this would just become g of 3x times 3 minus g of 2x times 2. And so that would end up being 3g of 3x minus 2g of 2x. That'd be my answer. And you're like, well, wait a minute. What if it wasn't just g of t? What if it was like sine or something? Sine of t. I don't know. What about it? Okay. This is going to be sine of 3x times 3 minus sine of 2x times 2, or in other words, 3 sine 3x, which is, by the way, what we just said here, minus 2 sine 2x. Again, what we saw right there. That'd be our answer. Okay? Pause you for just 1 minute. Okay. Here's a couple examples from the homework, kind of a problem. So here's one here, or similar to homework problems, I should say. So this one here, it just says that f of x, this is little f of x, my apologies, little f of x is equal to x plus 1 over x squared plus 9. I'm interested in what is happening. I'm interested in finding f of 7 equals 0. Okay, that's kind of what I'm interested in. What it wants me to do is it wants me to express the antiderivative of f of x satisfying the initial condition. So in a situation like this, what it wants me to do is it wants me to find the antiderivative. Yes? Well, that's pretty easy. So this guy here isn't too terrible. Of course, I picked one that's a little harder than I wanted to, but that's life, I guess. It's good review for us. Okay? So you may or you may not remember these guys. This one here is use U substitution for that guy, yes? So du would be 2x dx. So you usually have a half of a du, yeah? So you'd have a half, and then it'd be 1 over u du, which is going to be a half of an ln of u, but u is x squared plus 9. Plus, you may remember this fella. It is going to be an arctangent function. I'm going to go ahead and work it through the way I would do it. Some books teach you to memorize it. I don't know. If you can, if you want to, you're better than I am. Go for it. I personally have a hard time remembering my own name half the time. So if I have to do more work, it really confuses me and it makes me sad and weird. So you can do it a couple of different ways. You could do it like that. Or you could say to yourself, let's let x equal 3 tangent theta. And we do a trig substitution problem here. So we could have done it one of two ways. I could have gone the way I was starting to go, or I could do it this way. Whatever makes you the happiest makes me the happiest. Okay? So this ends up being 1 over, this is going to be 9 tangent squared theta plus 9 times 3 secant squared theta d theta. And on the bottom down here, you know, you put this on top if that makes you happier. Makes me happier. You can factor a 9 out and you'll get secant squared. Or sorry, you'll get tangent squared theta plus 1. This right here is secant squared. Yeah, that's just what it is. So you'll end up with 1/3, and then this is just secant squared theta, so they'll cancel out. You're left with just this. Well, what does that integrate to? It's 1/3 theta. And you're like, well, that's nice, Jay. What does that mean to me? Well, remember, this is trig substitution. So up here somewhere you said, let's let x equal 3 tangent theta, which is equivalent to saying that x over 3 is the tangent of theta. Right? So x, 3, x squared plus 9 square rooted. So here's my question though. What is theta? Theta would be the arctangent of x over 3. That's what my theta would be. Now, what have I just found? I have just found the antiderivative. And that's fine, but I'm interested in knowing what is it when f of 7 equals 0. What is the value of this constant? Okay, well, I don't know. But I do know I could do this. 1/2 ln of 7 squared is 49 plus 9 plus 1/3 arctan, 7 over 3 plus c. We know this whole thing has to equal 0. Right? That's literally what it said. So I'm going to break out my calculator here. Come on, give it to me. Come on. There she comes. Good. So I'm simply going to go 0.5 ln. 49 plus 9 is 58. I don't need an absolute value because it's positive already. So it's not a big deal to me in that point. 1/3 arctan of 7/3. Make sure you're in radians for what it is I'm doing. You'll notice I'm in degrees. I'm going to go ahead and hit enter. That's not the right answer. I need to be in in radians rather to pull this off. There we go. So 2.41. So this is 2.41 plus c equals 0, meaning c is equal to negative 2.41. Meaning that my final answer is this thing right here with a negative 2.41 on it. This is cap f of x. That's it right there. We'll do another that's not so gross. Suppose you had this function. Oh, pardon me. 3x, I don't know, sine x, because I feel like it, I guess. And actually, that's not what they said. They just said, here's your function. Cool, here's little f of x. And they said f of 0 is equal to 2. Can you find the constant? And I think I can. So, first things first, I need to integrate that thing, right? Pull the 3 out. Do you remember how to do this one? Remember, it's integration by parts. Right? Cosine goes to minus sine, so sine came from negative cosine. Correct. So remember, it's uv. So it's uv minus the integral of v du. Nope, there's no dx there. These are both negative, so I'll make it a positive here if that's okay with you. Okay. Where did cosine come from? It came from sine. So I'm just going to leave it like this for a minute. Multiply the 3 through, and this would be your final answer, sort of. right? That's my function. That's f of x, sort of, right? But specifically, I'd like to know at 0 that it's equal to, what did I say? It's equal to 2. So check it out. If you plug 0 into here, what happens? You get 0. You plug 0 into here, you get 0. Plus c equals 2. That means c equals 2. This means this thing right here is your final answer. Okay? Not too tough, I don't think you'll find. Okay? Here's one that your book likes to throw at you to see if you're paying attention, I think, more than anything else. It is what it is. Cool. So this is, I only drew those in for reference there. This is your actual function. Let's see what it asks for. So this thing is asking for this. It says this is y equals f of x. In other words, it is the derivative. Are you with me? So this is what we're saying here. Calculate a of 2. So a of x is equal to the integral from 0 to x of f of t dt. Now notice we're not taking the derivative of this. This is an area function, is what that's saying to us. Okay? So if I said to you, hey, what is a of 2, for instance? Well, it'd be the area under this curve from here out to here. Okay? What would that area be? Well, this is 2 units high and 2 units long. This answer would be 4. And you're like, well, how would I do that with this actual function? I see the picture there, Jay. Well, it would look like this. It'd be 0 to 2. And then the function would just be 2 dt. Are you with me? It's just a constant y equals 2. So then this would be equal to 2t from 0 to 2, which would be 2 times 2 minus 0, which is 4. Now you might say, well, what is a of 3? Well, a of 3. Well, that would be equal to a of 2, is that correct? Plus the integral from 2 up to 3, is that true? In other words, I need to add this little skosh on right here, yes? Now this line here has a slope of 1. That means it's a linear function. Looks kind of like that. Are you with me? So we know this piece here is 4. That didn't change. Plus, this is going to be t squared over 2 from 2 to 3. So that's 4 plus 9 halves minus 4 halves. So 4 plus 5 halves should be 6.5, I think. That would be the area from here all the way back. Now, interestingly enough, what would A4 be? Well, A of 4 would be a of 3, right? Plus the integral from 3 to 4 of t dt. That's one way to do it. Another person might say it's a of 4, and then it's equal to a of 2 plus the integral from 2 to 4 of t dt. That would also work. In other words, you could find this entire thing in one piece. That's this bottom one. Or you already know from here back, and you're only interested in finding this little sliver out there. Either case, that's how you'd find that. That to me is a kind of a fun problem, and it basically sees if you're paying attention to what's happening there. Okay, let me give you a couple more of these, and then we'll kind of see where we end up, and we'll move along. This one always makes me happy. It happens on so many of these works. It doesn't matter who wrote the book. It's like in every book. It makes me happy, though, because people don't pay attention and they mess it up, and I just kind of, whoops. So I'm going to take the derivative of an integral. So my answer is going to be the sine of 1 over x squared, something like that, yes? Times, oh, geez. Hey, what's the derivative of 1 over x? Okay? Remember, 1 over x is x to the minus 1, yes? And the derivative of that is negative x to the negative 2. So I need to keep the chain rule in mind. So my final answer should be something that looks like this. Negative sine of, and I could write as 1 over x squared inside there if I wanted to, over x squared. Okay? Here's another one that cracks people up all the time. So you take the derivative, but before you do that, you need to switch your limits of integration and negate the problem. So our answer is going to be negative square root of 3x times 3. In other words, negative 3 square root 3x. And that would be your answer. Okay? Those are the sorts of problems that you will be doing in this chapter, again, section 5.4. Again, so the two pieces of the fundamental theorem of calculus. Number one is this guy. You're going from a to b of f of t dt, arguably the most important part of it from the standpoint of what we use every day in calculus. Part two, and again, I don't really care which order you number them in. It's not a big deal to me at all. Part two is this piece right here. Okay? And what a person can actually do, and what I think your book actually shows up here, is let's call this a function of x. What? And let's maybe not make it f, because that'll freak everybody out. So let's do this. So these guys, the integral and the derivative cancel out, and so I'm left with f of g of x times g prime of x. That's how most books write it. Now again, if this function up here was just x, this would just be x, and what's the derivative of x? Just 1. Okay? This is the big deal, and again, your book does it in 5.3 and then in 5.4. Most books put them in the same section because they are the same stuff. But that's all. Two sides of the same coin, if you will.